Hey guys, Mr. McKinney here, just going through the squeeze theorem, which is sometimes known as the sandwich theorem. And we got this nice picture of a sandwich to help you remember the squeeze theorem. And the idea is basically that one function is getting squeezed or sandwiched in between two other functions. So here is the premise for the theorem. If everything above this yellow line is true, then we can conclude this piece right here. So if the function g of x is less than f of x is less than h of x, for all the x values near a specific x value, the one that we're going to be looking at, and the limit as x approaches c for g and the limit as x approaches c for h are both the same value, then the function that's in between g and h will also be approaching the same value. Now keep in mind this is all limits. So in language we'd say if f of x is between g of x and h of x, and g of x and h of x both approach the same value, then f also approaches that value, which makes sense. And if you look at a graph, it will make sense. So h is always bigger than g, and f is always in between h and g. So at c, both h and g are approaching the same value, this limit value. Now, if f is always in between them and both h and g are approaching the same value, then the squeeze theorem says that f must also be approaching that same value. Now, keep in mind that the sandwich theorem or the squeeze theorem only has to do with limits. It's not the actual value of the function. We're talking about limits. All right, so that's it for the squeeze theorem. Let's look at how it would get applied on the AP exam and then how it could be applied in a broader context. So the first year I taught AP Calculus was 2019, and on the very last question of the exam, on the very last part of the very last question, on part D down here, the squeeze theorem popped up. And I didn't cover it very well my first year, so I'm pretty sure none of my students got this part right, but my guess would be that less than 1% of students nationwide earned this point, and we'll talk about why. So it gives me f, g, and h. They're all twice differentiable, which means that they're continuous and differentiable, and then the derivative is differentiable. And it tells me a couple of values of g and h, and then it tells me that this line is tangent to both g and h at that x value. Now, we're going to skip over parts A, B, and C because they don't include the squeeze theorem at all, and just talk about part D. So it's known that g is always less than h between 1 and 3 for x. Let k be a function such that k is always in between g and h. So right here, this is the part that's telling me it's probably having to do with squeeze. For 1 is less than x is less than 3. Is k continuous at x equals 2? So to answer a question about continuity, remember that we need to know that the limit exists and the function exists and they are equal to each other. So the squeeze theorem can help us with the limits portion of that, but it won't help us with the actual function. We'll have to talk about that separately. And then we need to show that the limit and the value of the function are the same. Now the value of the function is just given to you in the problem because we're talking about x equals 2. So the squeeze theorem would be applied on part D down here. And altogether, with a whole bunch of writing, you can only earn 1 point. So don't get too bogged down on trying to write everything out because it's only worth 1 point on something like this. All right, so this would be the explanation for part D. And like I said, all of this explanation altogether gets you 1 point. So it's not worth spending a ton of time trying to earn points dealing with this type of problem. But it will potentially show up on the AP exam, so I'm going to talk through it. All right, so first of all, we need to talk about the fact that g and h are going to be continuous. And we know that because they are differentiable. And because they're continuous, we know that the limit value for each of them is equal to the function value. And they gave us the function value in the original problem. So we can show that the limit for g as x approaches 2 and the limit for h as x approaches 2 are both equal to 4. And then the problem told us that k was always between g and h. So the squeeze theorem allows us to talk about the limit as x approaches 2 for k. So because g and h both approach 4 as x approaches 2, and k is trapped in between them, k will also approach 4. Now keep in mind that the squeeze theorem only talks about limits. In order to be continuous, you need to have a limit and it needs to be equal to the function value. So we also need to talk about the function value. We knew that g of 2 and h of 2 are both equal to 4, again from the original problem stem. And we know that k is in between them, therefore k must also be equal to 4. K of 2 would be equal to 4. So since k of 2 is equal to 4, and by the squeeze theorem, the limit as x approaches 2 of k of x is also equal to 4. Because these two things are equal to each other, we're allowed to say that k is continuous at x equals 2. So again, a lot of work to earn 1 point. But the squeeze theorem has to do with limits, and it says that if two functions approach the same value and there's a function trapped in between them, it will also approach the same value. For those of you guys that are interested in proofs, you can keep watching. If that doesn't sound interesting, you can go ahead and log off now. But I'm going to go through an example involving proofs. I've also got the key for A, B, and C up here if you guys are curious, so you can hit pause and look through and see if you guys did it right. All right. So here are some area formulas that we'll be using in the proof that's coming up. So if I want to find the area of a sector, it's 1/2 times the radius squared times the angle. And if I want to find the area of a triangle that is not a right triangle, it's 1/2 times A times B times sine of the angle in between them. So if I want to prove that the limit as x approaches 0 of sine of x divided by x is equal to 1, I can use those two area formulas along with the squeeze theorem. I'm going to show you guys that in a second. Now, you would not want to do this on the AP exam. Since we get a limit on the top that approaches 0 and a limit on the bottom that approaches 0, you guys would approach this as an LHOP problem. But if you wanted to prove it or you want to see how the squeeze theorem can be applied, this is what it would look like. Uh-oh, my image didn't make it in. All right, I'm going to get that image real quick. All right, hopefully I fixed it. All right, here we go. All right, so we know that the area of this blue triangle is always going to be less than the area of the sector, which would be the blue triangle plus this little purple section, and that sector would always be less than this triangle that I can draw that would be a right triangle. We're going to call it triangle OAD, so OAD. All right, so for the blue one, we can use that formula that we just talked about, 1/2 times A times B times the sine of C, and in this case, C is the angle in between them, so it's going to be x. Both A and B on this triangle are 1. So that's for the blue triangle. For the purple sector, which would be this little purple sliver plus the blue triangle, it's 1/2 times the radius squared times theta. And again, theta is x. The radius is 1, so we've got 1/2 times 1 squared times x. This last one is a right triangle. So we can just think about it as the area would be 1/2 base times height. Here's my right triangle. Base is 1. Height is this distance, which we're going to call b. That's this little b over here. And we can figure out that b is equal to tangent of x if we set up a ratio here. So the opposite side would be b, the adjacent side would be 1. So tangent of x would be b over 1. So b is just equal to tangent of x. So that's what I'm going to plug in over here. Now, they use this formula. Sine of 90 is 1, which is the same as just using 1/2 base times height for a right triangle. So that's why this part goes away. All right, so now we're down to this part. 1/2 sine of x is always less than x over 2, which is always less than half of tangent of x. Then I can multiply by 2. I can rewrite tangent as sine over cosine. And then I'm going to flip everything. So sine becomes 1 over sine, x becomes 1 over x, and then this one, when it flips, it becomes cosine over sine. Now, if I take reciprocals with inequalities, I also have to flip the symbol from less than to greater than, or vice versa. So both these less thans turn into greater thans. Now I can multiply the whole thing by sine. So I'd get 1 is greater than sine of x over x, and this is the thing that we're trying to prove. And then when I multiply by sine here, it cancels out. And then I can rewrite this whole thing instead of going from like left to right, basically going from right to left. So cosine of x is less than this middle term, is less than 1. And now we can start thinking about limits. So the limit as x approaches 0 of this would have to be less than the limit as x approaches 0 of this, which would be less than the limit as x approaches 0 of 1. Now these first two, we can figure out that those limits are both equal to 1. And so if this limit is always trapped in between 1, then it must also be equal to 1. Now again, we would not use this on the AP exam. We would use LHOP. Write out a separate limit statement for the top and the bottom. So make sure you write out two separate limit statements. Don't try to write it as one. And then you can reference LHOP, and we would do it that way. But this is another application of the squeeze theorem. All right, hope this was helpful. Have a great day.